Okay, now that we've done some ray tracings, now what I want to do is look at some equations involving the object distance, the image distance, and the focal length, whether we're talking about a lens or a mirror. I'm going to derive the famous object image formula for the mirror. It turns out it has the exact same form for the lens, but I'm not going to derive that one. All right, so I'll do the mirror one, and if you want to look at the lens one, just read the book. It's in the book. There's a lot of approximations made, and it's kind of long, and I really don't want to go through it. But if you're interested, please go ahead and study carefully the derivation. So I want to derive the object image formula for the mirror. It's pretty straightforward. So what I have drawn, what I have on the screen here, is an object in front of a mirror, and I'm also showing you the location of the image. And so we're going to do a little bit of geometry here. So here's the object. The object height is A for the time being. And then the image height we'll call B. And you'll see different names for the object and image, the object height and the image height. So it's not standard. In fact, neither is the image distance and the object distance a standard. That's not standardized either. But let's go with what we have here. So the distance from this object to C is called S naught. The distance from the image to C, the vertex there, is called S sub I. That's the image distance. What I've drawn is a ray that goes from the top of A, the top of the object, reflects off the vertex towards the image. This is one of the rays you can use for ray tracing. And because of the law of reflection, this angle here and this angle here have to be equal. Now we have two triangles. We have two right triangles here. This is a 90-degree angle. This is a 90-degree angle. And then we have these two angles in common. Well then, since the sum of the angles in a triangle always adds up to the same number, 180, that means that this third angle here in this triangle and this triangle have to be the same. So triangle ABC is similar to triangle DEC. So we have two similar triangles. What that means then is the ratio of B to A has to be equal to the ratio of S sub I to S sub naught. The ratio of B to A is equal to the ratio of the image distance over the object distance. So I'm going to write that on the board real quick, because that's going to be one of the equations we're going to be working with. So let me write it on the board. So we'll write B over A is equal to S sub I over S sub naught. Okay, just going off this diagram. Now I'm going to use this same scenario, but I'm going to draw a different set of triangles. And you'll see it in this slide. Now I want to look at this triangle here. Now this line that you see will actually pass through the top of object B. So we're going to look at this angle phi and this angle phi. We want to look at this triangle. This is the focus point of the mirror. The length of the base of this right triangle is the object distance minus the focal length of the lens. This is the height of the triangle. And then the other triangle I want to look at is the one right over here. You can't see the other one, but the line here, I didn't want to draw the line here because it would be confusing if I drew the line on the mirror itself. But there's a line here that's perpendicular to the principal axis. Its height is b. This distance is f. This triangle is similar to the big one because you have the 90-degree angles in common. You have phi in common. That means that third angle has to be in common. Because the triangles are similar, we can say that A over B is the same as the ratio of this distance over that distance. So let's write that on the board. So we have A over B is equal to S naught minus F over F. But if B over A is this, and A over B is S naught over S sub I. And let me look at this equation right here. This is the same thing as writing S naught over F minus, well, F over F, which is 1. Let me divide both sides by S naught. And what do I get? I get 1 over F minus 1 over S naught equals 1 over SI. Rearranging this, I will get 1 over S naught plus 1 over SI equals 1 over F. This is the object image formula for the mirror. It turns out it's also the same equation for the lens. 1 over the object distance plus 1 over the image distance is 1 over the focal length of the lens. That's going to be our working equation for a lot of the problems we're going to be doing in this chapter. Now, we saw earlier that the ray tracing will allow us to find the image, the location of the image. This equation is going to be more accurate for us. So there's our equation. S naught is the object distance, SI is the image distance. F is positive for a concave mirror. F is negative for a convex mirror. For a lens, F is determined by the Lensmaker equation, although I'm generally going to quote the value of F in a problem. I'm not going to really hold you responsible for the Lensmaker equation on the exam. You might need to use it in the homework once, but you're not going to be responsible for it on the exam. The Lensmaker's equation basically just allows you to calculate F given the index of refraction of the material and the radii of curvature of the material. Now, another thing that's important is the quantity 1 over F. The quantity 1 over F is the refractive power of the lens in diopters. 1 over the focal length in meters. Your optometrist uses this when they give you a prescription for your contact lenses or your glasses. If you look at their prescription, the prescription's in diopters. Okay. So this is our main equation. I want to say a couple things. Like I said, S naught is the object distance. Not every book goes by that convention. A lot of times people use P. Some people use just the letter O. There's no convention for this, unfortunately. Okay, our book uses P and Q. So P, so when I write S naught or P, that means the object distance. And every time we change a textbook, those letters change. But these are the most common ones. And then S sub I can be also rewritten as Q is the image distance. But all books use the letter F for the focal length of the lens or the mirror. Okay. This equation works for both the mirror and the lens. Like I said before, I am not going to derive the equation, this equation for the lens. You can read the book. Okay, so another thing we define is called a magnification. That ratio that we saw earlier, this ratio of the image distance over the object distance, which is really the image height over the object height, is the magnification. However, we put a minus sign in front by convention. Most books use this convention. There's one book that I know that doesn't use this convention, but most books use this convention. We use the letter M for magnification. We write a minus sign for in front of it. And really the minus sign has to do with the fact that if you produce a real image, the object is, the image is upside down. The minus sign just tells you that the image is upside down. Okay, that's why that's there. Okay. Or you can write it as the image height over the object height. Okay, image height, object height. You can write it like that. This is the absolute value. It's written like this again. The minus sign is just there to tell you whether or not the image is inverted. So, if you produce a real image, this number is positive, this number is positive, and the magnification is negative. The image is upside down. But if you produce a virtual image, this is negative. And then a negative times a negative gives you a positive. That tells you that the image is right side up. Okay, so for a virtual image, SI is considered to be a negative number. Why? Well, if you have a lens, you have an object here and the image is over here and not on this side, we call this, we say that this distance is negative. Same thing with a mirror. If the object is here and the image is here, this is a negative number because this image is located on the wrong side, right? For a mirror, the real image has to be on the same side as the object. For a mirror, for a lens, the image has to be on the opposite side. If it's on the same side, the image is negative. Here, if the image is on the opposite side, the image is negative. Okay? Now, when you're using this equation, this is confusing. If I want to solve for the height of something is a positive number, right? There's no such thing as a negative height. If I want to use this equation to solve for the height of the image based on this equation, I need to use the absolute value of this. So to solve for To solve for either one of these two, you need to use the absolute value of m. So you got to take the absolute value of that. Otherwise, you might get a negative number. Heights aren't negative. How tall are you is not a negative number. It's a positive number. All right. So if the magnification again is positive, the image is upright. If it's negative, then it's inverted. And if you have only one optical element, and like it's a lens or a mirror, if the image is inverted, it's a real image. If the image is right side up, then it's a virtual image. That's assuming I only have one optical element. All right, let's do an example. A distant object forms an image 15 centimeters in front of a concave mirror. Where will the image be located if the object is placed 25 centimeters from the mirror? Assuming the object is 2 centimeters high, what is the image height? What is the radius of the mirror? All right, let's do this problem. It's not too complicated. And let me write my object image formula here. And I guess I should write my magnification formula too. I'll write it like that. Okay. All right, so where are we given? We're given in the problem the image distance. So in the problem, we're given the image distance. So we're given S sub I equals 15 centimeters. We don't know F. Or do we know S naught? It says, well, how am I going to be able to solve this? I don't know the object distance. Actually, I do. Because it says in the problem, a distant object. What does distant means? It means it's really far away. This is a very big number in the denominator. What is 1 over a very big number? It's about 0. The lab that you're going to be doing, you're going to be using the distant object method to measure the focal length of a mirror and a lens. So this, we're going to let S naught be big. That means that 1 over S naught approaches 0. So what that leaves me is 1 over SI equals 1 over F. Oops. So SI is 15 centimeters. Right, the only way that this for V equals is that SI equals F. So the focal length of, the focal length of the lens is 15 centimeters. Now, where will the image be located if you place the object 25 centimeters from the mirror? Okay, so now let S naught equals 25 centimeters. What is S sub I? Well, this is pretty straightforward. I mean, all I got to use is this equation. I have 1 over 25 centimeters minus 1 over SI equals 1 over 15 centimeters. And really, the way this equation is, you can use centimeters or meters. Doesn't matter. So, oops, I forgot. It's a plus. Sorry. I just solve for 1 over SI. 1 over S sub I equals 1 over 15 centimeters minus 1 over 25 centimeters. This is easy to do in your calculator, but if you're not doing it on your calculator, you got to get a common denominator. And I can see the common denominator is 75, because 15 times 5 is 75. And 3 times 25 is 75. And this gives me 75. 2 over 75. So 1 over S sub I is 2 over 75 centimeters. I take the reciprocal of that, so S sub I is 75 over 2, which is 37.5. And that's my image distance. What's my magnification? My magnification is minus 37.5 over, what was the image, what was the object distance? 25? And that comes out to about 1.5. Actually, negative 1.5. The minus sign tells you that the image is inverted. And if I want to find the image height, I got to take the absolute value of this. Or I can just use the equation like this. H naught is 2 centimeters. 2 times 1.5 is 3. Now, what is the radius of this mirror? Well, the focal length is R over 2. So then R is 2F. So R is 30 centimeters. The ray tracing, okay, if you're going to do ray tracing, you got to do it to scale. It's harder for me to do it to scale on the board, but we'll just draw one anyway, okay? So these are the values. Let me erase. So I'm going to freehand one because I'm on the board. In general, you don't want to do that, right? You want to do it to scale. Ray tracings are drawn to scale. It's not like a free body diagram, because this allows you to determine an image distance. Okay, let's do a ray tracing for this. Here's my black marker to draw my mirror. This is 15 centimeters. And twice this distance. That's the center. I guess that's close enough. And let's put the object right over there. Like I said, this is hard to draw to scale when I do it freehand. So we'll start with parallel before. Focus point after. Focus point before. parallel after. And then the one that goes through the center, that one's hard to draw because the object is inside the center. So that one's hard to draw. I mean, we can try to draw that's not very good. So the image is about right there. So that would be the ray tracing for it. And again, for me to draw this on the board is very challenging. Okay, but if you do it on paper, it's way easier because you need to draw it to scale. It's very important that you make these to scale. Let's do another example. But this time, let's do it with a lens. In this case, a distant object forms an image 25 centimeters in front of a double convex lens, and we want to find where the image will be located. And we'll draw a ray tracing. A very similar type problem. So here we go. So let me erase this. Let's see, we're given that a distant object forms an image 25 centimeters in front of the lens. Well, that means that the object distance was really large. This is 0. That means 1 over SI equals 1 over F. That means SI equals F. So the focal length of this lens is 25 centimeters. And we're going to let S naught equal 15 centimeters. This tells me right away we're inside the focal length. We're going to get a virtual image. We'll use that equation. And without putting the numbers in, I can just solve this for S sub I, or 1 over S sub I. So I put in 1 over 25, like so. And again, I'm going to get a common denominator of 75. So 3 over 75. Three minus 5 is -2. And so S sub I is minus 37.5 centimeters. Okay, so what is the magnification? It's minus SI over S naught, so let's put minus 30. Minus a negative is a positive. S naught is 15. This becomes plus 2.5. So the image is 2.5 times the size of the object. So the absolute value of M is HI over H naught. is equal to 2.5. If this is 2, 2 times 2.5 is 5. Let's draw ray tracing. Now in a test, you're going to have a grid, so it's much easier to do the ray tracing. I don't have a grid here, so I'm going to have more of a challenge in drawing this. So here's my lens, and my focal length is 25 centimeters, and my object length, object distance is 15 centimeters. So let me draw these in here. Try to be as accurate as I can, doing this by hand. And then let me draw my object. Okay. So I'm going to do parallel before, focus point after. Focus point before, parallel after. And then one through the center of the lens. Now let me extrapolate. You can tell these are not going to converge. On this side, they're not going to converge. So let me extrapolate the rays backwards. Let me extrapolate this one backwards. And let's extrapolate the other one backwards. This one's going to be tough. That's pretty close. And so the image is right there. That's the location of my image. It's bigger than the object, which is what should happen. Alright, that's it. That's how you draw the ray tracing. If this were a concave mirror, you would have a similar drawing, except that the image would be in the opposite side of the mirror. Now, one of the things you need to learn is to really study the characteristics of the image formed by a single optical element. If you're between one and two focal lengths, the image will be bigger than the object. And that's the case for a double convex lens or a concave mirror. I should be careful. Okay, if I have a double convex lens or a concave mirror, if the object is between f and 2f, the image will be real, it'll be inverted, and it'll be larger than the object. If the object distance is greater than 2f for a double convex lens or a concave mirror, then the image will be real, inverted, but smaller than the object. If you have a convex mirror or a double concave lens, the image will always be virtual. So you need to understand these things. Okay, you need to understand the characteristics of the image form. Now granted, this is just with one optical element. Okay, we're just talking about one optical element here.